Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Today, we are going to finish this part that was a bit boring, I know, because it's more like historical accumulation of all the findings and the great ideas that people had when they were building these systems. So it's more like a collection of good ideas. Let's put it this way. So I'm going to finish this. Then I'm going to talk about the big picture of an information retrieval system, and then we'll move over to the matrix. So we were left with this ranked retrieval, which is about using the vector space model in order to rank results. That's new. We didn't have this before with Boolean retrieval. And we need the concept of score. And in order to have scores, what I showed to you is that we can compute the score of a document by just summing over the TF-IDFs of all the terms that are in that document. So what are TF-IDFs? What does it mean, TF-IDF? Anybody on Zoom, maybe? What does TF-IDF mean? Giving you some time to wake up, get back into the context. Yes, go ahead. Yeah. Yeah. Yes, exactly. So the TF, I'm repeating because you didn't have the cube. TF is term frequency. It takes two parameters, the term and the document. It's bidimensional. The inverted document frequency, IDF, is for a term. It's only indexed by terms because it's over all of the documents. So there's only a T as a subscript. And TF-IDF is just the product of these things. And TF-IDF has almost become a word, actually, just TF-IDF. That's the standard weight if by default, if you don't know anything else. And what we do is that we accumulate the TF-IDFs for a fixed D. D is the document for which we compute the score. And we just sum over T of the TF-IDFs. And what we do is we traverse the index. It's an augmented standard inverted index, an enhanced version. And we just traverse it for all documents and terms, accumulating the TF-IDFs in the appropriate document buckets, depending on D. And we sum over that. And we saw that we can do it term at a time or document at a time. Term at a time means term by term and within a term across documents. And document at a time means we move in parallel across all of the posting lists at the same time. That's document at a time. But we can only do this if the posting lists are all sorted with the same sorting criteria, meaning the documents are in the same order for all terms. Otherwise, we can't. All right. So then we discussed optimizations, and the optimization consists in only computing these scores on a set of pre-selected documents. Not all of them, that would be too much. We pre-select some of the documents. We only compute the TF-IDF sums over them, and then we have an inexact top 10, which is actually quite good in practice. So all of the strategies consist in finding a way to select that subset of the documents on which we actually compute the score, to pre-select them. And so what we were left with in the end is to give you an idea of the general paradigm, is that you might want to sort the terms in your standard inverted index, not alphabetically, or you can still maintain the alphabetical structure to look them up, but you want to sort them by decreasing IDF, meaning the ones that are really rare and relevant on top and the stop words at the bottom. So you sort by IDF. And here you sort by term frequency. So I have these little bars that just indicate the term frequency. So the documents that have the most occurrences of the term come first, then it decreases. And then what you do is you basically start here with the most frequent, the opposite, the most rare term, and you start with the documents that contain that term a lot of time. A rare term that appears a lot in a document, probably a very relevant document. And you basically go on diagonally, you basically try to get more terms that are a bit less rare, more documents that contain them a little bit. And basically, everything that's relevant is in the top left, and everything you don't care about is in the bottom right. right? Because these are the terms that are really rare and useful, and these are the documents that contain them a lot. So these are super high scores probably. And then this is less, this is also less. And here, that's really what you don't want. These are basically stop words and stop words that don't even appear in documents. So this is really what you don't care about. And basically, you just have to find a compromise between going a bit here, going a bit there, then moving like this. And basically define the zone in which you actually want to compute the TF-IDFs. And for the outside the zone, you just leave them out. So this is the idea. Can we do that with a term-first approach? Can I do this, apply this scheme with a term-first approach, term by term? I can, right? What about document first? Can I actually do this document first? Who thinks I can? On Zoom, anybody? Who thinks I can? Nobody? Who thinks I cannot do it? Ah, a couple of raised hands. Yes, higher the hands. You're right about this. And why can I not do this document first? Yes? Yeah. Exactly. You would need them to be sorted by document IDs or by whatever is independent of the term. This is why, right? They are sorted here by term frequency. And because of that, this is not the same order in every term. So you cannot do it document first. But term first, you can always do that, right? So it only works with term at a time. Term first, term at a time. Term at a time and document at a time. All right. Makes sense? Everybody's with me? Okay, this is actually it. So this was just the final thing I wanted to show you regarding these optimizations, and just a few words on going a bit in the direction of machine learning. But another way to pre-select documents is, again, to go back to this vector space with the idea that the documents are nothing else than vectors in a very highly dimensional vector space and only in the first quadrant. And what you can do is pick random documents called leaders. You basically take the square root of that. So if you have a million documents, you're taking 1,000 of them. And then you build clusters based on the angle, right? You just divide your quadrant in angles. So of course here it's two-dimensional, so it's trivial to do, right? If you are higher dimensional, it can get a bit more tricky. Even in 3D, the notion of 3D angle is a bit tricky, but you get the idea, right? So you basically have these clusters, but these are clusters of angles from the origin. And when you have a query, you just look for the closest leader by Euclidean distance, or no, not by Euclidean distance, based on the cluster in which it is. So you just look at the cluster in which you are, pick the leader, and you pre-select all the documents that are in there, right? Okay. I wasn't incorrect on Euclidean distance. As long as you take the Euclidean distance on the normalized vectors, the unit vectors, then it would be probably very similar. All right. So now, what if we get less than 10 documents because we pre-selected in order to facilitate the computations, and then we don't even get 10 documents? So that would be a problem, right? So what do? There are also tricks for that. And the tricks consist in splitting the postings list like this. So we have a high list and a low list. And the idea is that you separate these postings list into 3 or more parts like this. So you have a standard inverted index with only the high lists, the first part of the documents when you sort them by decreasing TF. Then the tier 2, the middle part, and tier 3 is the low part, right? And then what you do is that when you have your query, you pre-select based on the tier 1. Do you have enough results? Yes, then that's fine, you stop. Do you not have enough results? You go to tier 2 and accumulate more. Do you have enough? Yes, then you stop here. If you still don't have enough, you go to tier 3, right? So this is the way of falling back until you get your 10 top documents or 10 or whatever other value you want. All right? Okay. There is also something mentioned in the book that is an alternate way of scoring, which is based on proximity. So it's mentioned as maybe as a curiosity. It's a bit of a different approach. It's the idea that if you look for ETH Zurich, you look how far away they are, right? And in order to do this, of course, you need a positional index, as we saw before, that contains the positions of the tokens, like we had for phrase search. And then you compute the distance. So ETH Zurich in the first one is very relevant. They're close to each other. Then you have one of the two Swiss ETHs is in Zurich. So that's less relevant, but still relevant. And the third one is their active ETH cryptocurrency. There's an active ETH cryptocurrency ecosystem in Zug near Zurich. This one is probably less relevant. It's not even the university ETH Zurich, something related, right? So then you basically sort them and pick the top two based on that. For example, just an example. But you can use also this notion of distance between the worlds as another way to score. Nothing to do with TF-IDFs here, just another approach. Okay, now wrapping it up. We've looked into a lot of things, right? We looked into Boolean queries, how to handle wildcard queries, how to handle phrase queries. We looked at the vector space model with sets of words, bags of words, and so on and so on, field zone queries with zone indices, and so on and so on and so on, right? So we really did a lot of things. And now, how is it put together in a big system? Well, it's kind of going to be a mix of a little bit everything. So what do we have in a final system that is actually in production used by people? Well, we have a part that has the document cache. This is the part where you download the internet, right? So you download everything, you read through the entire collection, and you put the documents in some cache. You probably noticed if you use a search engine that even if the website is unavailable, you sometimes have a small link like view in cache, and they will actually still show you the document as it is in the cache. So this is what it does. And this is the part where you also parse the document and prepare it for the indexing. Then you index. So we've seen a lot of indices, the standard inverted index, the permuterm indices, the positional indices, the byword indices, keyword indices, the augmented indices with the TF-IDFs and so on. So when you build a system, you don't have to choose one, you just do plenty. So you could have several indices, zone indices, I also showed you, inexact top K, tiered inverted positional index, byword, K-gram, and so on and so on and so on. Which indices you pick depends, it's whatever you want, right? But typically several of them, and then you build them. Once you have built your indices, you are ready to serve your user. So the user queries come in, right? And you can either parse the query as free text, you can parse as Boolean query or whatever, do some spelling correction, and then you look up in the index the documents you want. If it's a Boolean index, it's just an intersection or union, as we saw. If you want to use the ranked retrieval, then you are going to accumulate the FIDFs in the index. So, but you basically use the indices and do what you're supposed to do with the index that you use. And you do it with all indices, not just one, several indices. You just try to look up everything you can in all the indices. And then what happens is that out of all the indices, you accumulate scores from the TF-IDFs, maybe also from with the spelling correction, the K-gram indices, and so on. This is called evidence accumulation. You squeeze out of the indices as much evidence as you can, whether documents are relevant. You accumulate scores for the documents through all the indices you can, and then you use that in order to rank the documents. There might be also a weighting system. For example, you might want to say, okay, I want to overweight the ranked, the vector space model system and maybe care a bit less about the byword indices, or on the contrary, maybe I want to give more weight to the K-grams and a bit less to the tiered index. So you can have different weights in there for the score. So there are ways to tweak the score. It's like cooking, right? When you bake a cake or something, you can put a bit more sugar, a bit more flour and so on. So this is all up to you, a bit more chocolate too in Switzerland. And so you can adapt the weights. These are like parameters, and then you get the scores for the documents, some documents, and then you return the results. This is also the part where you might to use the document cache to display the results. Why? Because you probably noticed if you search over the internet that it doesn't just give you a link to the results. You also have a snippet. It also shows you an excerpt of the document with the words shown in bold or maybe some yellow yellow marks and so on. So this actually comes from the cache. Because why do we need the cache? Because in the indices, if you use the set of word model, you lose the order of the words. You don't have them in the indices. So in order to display the snippet to the user and the words in context, you actually need to get back from the cache the actual original text of the documents. right? So this comes from the cache. Then this is displayed to the user. This is actually the Google websites that is facing the users. And finally, this part here about how do you determine the weights. This is when machine learning comes in, where you can actually train your data in order to find the appropriate weights in order to optimize your metrics, which we will talk in just a few moments. Okay, and this is how you score. That's it. That's the entire system is like this. And now probably everything we've been doing since now probably 10 weeks is adding up, like this is the whole system. And now all of this should be familiar to you. You probably should be able to build a system like that based on what we learned. Of course, it's a lot of work. If you want to actually build a production system, knowing how to do it is not enough. Then you have also the experience of actually building production systems with, containers, Kubernetes, and so on, right? But this is outside of the scope. Okay, who has a sense of familiarity with this view now, that everything we've seen? Okay, this is how it's all pasted together. Okay. Oh, that's the last slide. So I'm actually done with this part. Do we have any questions on this? On Zoom, questions? Okay, so congratulations, you made it through it's the hardest to teach part of the course because this is the most boring one, just an accumulation of things, but you're done. Now let's go to another super interesting parts with the matrix. So I'll be disconnecting the slides and be back in a few seconds.